All right, so we're going to first take a look at the exponential growth function, modeling exponential growth. So if given like a table, we can create an exponential growth function that models the data, and then actually using exponential functions. Okay. All right, so the exponential growth function looks like this. If you're going to have some y value will be equal to the initial y, and then e raised to the kt. Okay. Y sub 0 represents that amount present at time 0. All right, and you recognize that this kind of looks like that PERT formula that we did with continuously compounding interest with money. All right, same setup. It's just they're using different letters for variables, but it still means the same thing. So y sub 0 is the initial amount present, equals our y, which is the amount present at any time t. So if we have as a function of t, so t we go out 10 years, the actual y will tell us what the new value will be. K is a constant, and if k is positive, it's the growth constant, and if k is negative, it's the decay constant. So that's why I say exponential growth or decay. It's the same function. It's just you're going to have a positive k for a growth. You'll have a negative k for a decay function. Can you put that away, please? All right, so with that function, let's actually create a function to represent this data in the table. So the growth of carbon dioxide over time is modeled by this table. So in 1990, the amount of carbon dioxide was 353 ppm, stands for parts per million. So in 1990, the carbon dioxide level was 353. And then they're extrapolating the data, kind of predicting that in 2275, carbon dioxide levels will be at 2,000 parts per million. Okay, so they give us a table, and then we have to create an exponential function that models this data. Okay, so find an exponential function that gives the amount of carbon dioxide y in year x. Okay, so I'm going to start this out. I'll say then y will equal y sub 0 e to the k x. Rather than kt, they said in year x, so we're going to use x. All right, so I'm trying to create a model that if you tell me the initial amount, or I can look at my table and see the initial amount, you tell me any year x, and I will tell you the amount of carbon dioxide in parts per million. But we don't know k, so we have to use the table to be able to figure out what k is. Then we can actually create our function. All right, let's say we're just going to start as a baseline of 1990. We're going to consider that like year 0. So I'm going to say x equals 0 is going to represent 1990. And so I'm going to be going from 1990. So 2000 would be x equals 10, because 10 years past 1990. All right, so starting to create my function, my y sub 0 is what I have here, this initial amount, 353, e to the k times x. Okay. I am going to use this bottom row of data to actually figure out what X is. Or I'm sorry, try to figure out what K is. Okay? I know the amount of carbon dioxide is going to be 2,000. My initial amount was 353, so that stays there. E raised to the K times X. All right, so if X equaling 0 is 1990, 2275 would be X equaling 285. It's 285 years past 1990. Okay, so 2000 was 10, 2075 would be 85 years beyond, and so on. Okay, so we got to tack on essentially 10 more because we're going all the way back to 1990. Okay, so then this is 285. So now I have an equation, 2000 equals 353e raised to the k times 285. So now I want to solve for k. All right, so the first thing I would do, I would divide out this 353. So I have e to the 285 k. I have an unknown in the exponent, so I'm going to take the natural log of both sides. And by doing that, it allows me to bring that 285k down from that exponent position. So I have the natural log of 2,000 divided by 353 equals 285k times the natural log of e. Well, natural log of e is nice because that's 1. So doing all that eliminated the e from my equation. Okay, trying to solve for k. So all I have left is 285 times k. So I want to divide out that 285. So this would be natural log of 2,000 all over 53. All of that divided by 285 will get k. So you have a fraction in the numerator, natural log. You're not taking the natural log of 285. You're taking the natural log of 2,000 divided by 353, and that gets you k. Put that into your calculator. You get 0.00609. So final answer on this, the exponential function would then be y equals 353 e to this new k value that we found, 0.00609 times x. So we had to do all that work to figure out what k was using x's and y's that we already know. Now this function, if you told me out at year 5,000, I could tell you then what the carbon dioxide levels will be based on this table, based on this trend. Okay. Let's do a part B to this problem. Now from this, estimate the year when future levels of carbon dioxide will be double the pre-industrial level of 280 parts per million. Okay, so back way before 1990, that's when they say pre-industrial, before the industrial era when carbon dioxide levels were less, it was at 280 parts per million. Okay, so if this is going to double, if 280, if they want me to double this, I know I'm going to be at 560 because I want that 280 to double. So now using my equation that we found in part A, I'm going to say 560 now equals 353 e to the 0.00609x. So now I'm trying to figure out x, which represents the years. All right, same process. I'm going to divide out that 353. I know I'm going to take the natural log, so this would be 0.00609x times the natural log of e. So that goes to 1. So it's, there we go. It's the natural log of 560 divided by 353. Natural log only in the numerator divided by 0.00609. That will give me x, which in this case is 75.8. So we're trying to find a year. So when is this going to, so what year? So 75 year, what does that mean? And it's important, this is years, so 75.8 years. So we're only going to be working in years. So this is, we're going to treat this as 75 years. We're not to the 76th year yet. So during the 75th year is when it doubles. Okay? But remember, we're going all the way 75, so 1990 plus 75 years. Okay, so that puts us at 2065 is when it would have been double those pre-industrial levels. Okay, which makes sense here in our table, because at 2075 it's at 590. I'm trying to get to 560, so it had to be less than 2075. So 2065 makes sense. If you got 5,065, you made a mistake somewhere. Okay, if that makes sense. It would go right in here. All right, so this is how we can get to where we can solve anything, but first we have to come up with the model. Let's do another one. How long will it take for money in an account that accrues interest at a rate of 3%, compounded continuously to double? All right, so I got $5. How long is it going to take for that to turn into $10? I have $2,000. How long is that going to take to turn into $4,000? We're trying to figure that out. So this is that same exponential growth function, but for money, we're used to seeing it as A equals PE raised to the RT. Same thing. I mean, both are exponential growths. It's just the variables. What each piece means, we relate it to money easier when we see it as A equals P times E raised to the RT. Okay, so again, P is our starting amount. And so if I want to double that starting amount, I can say that it's going to be 2P, or 2 times P. So now I can say 2 times P equals P E raised to the RT. That final amount, I want it to be twice as much as what I started with, so I can write it just as 2P. Both of these are being multiplied, so 2 times P on the left and P times E raised to the RT. If I divided P out from both sides, it essentially goes away. If I took one of them and divided to the other side, I go to a useful form of 1, so I don't have to worry about that. So now I can just say 2 equals E to the RT, and I know R is 0.03, my R times T, and I'm trying to figure out what T is. We can do this with natural logs. So I'd say natural log of 2 equals 0.03 T natural log of E. That goes to 1. So natural log of 2 divided by 0.03 would equal T. And I work that all out, and I get 23.10. So how long will it take? Okay, I could say approximately 23 years for it to double. All right, we're gonna round to the whole years on these, but in the context. Okay, so it's into the 23rd year, but not far. We'll just say approximately 23 years. Okay, next thing we're going to talk about is half-life. So half-life represents the amount of time it takes for a quantity decaying exponentially to become half of its initial amount. So this is kind of the opposite of our doubling time that we just did. We're thinking, okay, what about half of that amount? And again, this is still using our exponential function, but because it's a decay, our k is going to be negative. So any half-life problems when you're solving for k, you need to get a negative number for k. Or when you're working with the actual model of the function that you create, k is negative. Make sure your k is negative. Okay, all right, so let's do an example of this. Suppose we have 600 grams of a radioactive substance. Our 600 grams of a radioactive substance are present initially, and then 3 years later, only 300 grams remain. Let's determine an exponential function that models this decay. So again, we're starting y equals y sub 0, e to the kt. Still using that exponential function. We're in this part A, we have to determine that exponential function. All right, it tells me after 3 years, 300 grams remain. So I know y is going to be 300. The initial amount was 600. E raised to the k, which we don't know, but t we know is 3 years. All right, so this one's similar to what we've been doing. We're trying to solve for this k, this unknown. So I could say 300 divided by 600 is going to be equal to e raised to the k times 3. If I take the natural log of each side, it allows me to rewrite this as 3k times the natural log of e, which is just 1. So we have the natural log, 300 divided by 600. I'm just going to write that as a half because that's the same thing. Divided by 3 will equal k. We'll work this out, ends up being a negative 0.231, which makes sense. I knew my k had to have been a negative value because it's a decay, it's a half-life problem. They want us to write a function, so we got to go back to our setup. I'm going to have y will equal, it's starting with 600, e to my k, which is negative 0.231 times t. So this function, from that, you give me a time in years, I will tell you how much substance is remaining. Okay, so we can use that in part B. I say, well, how much will be there after 6 years? And so y represents that amount that's going to be there. 600e to the negative 0.231 times 6. Put that right there in my calculator. and I have 150 grams remaining. All right, and then the last example, we're going to talk about carbon dating. So carbon dating is a way that they can look at substances they find and determine how old that substance is. So the amount of radiocarbon present after T years is given by this function. So somebody somewhere along the lines created this function, or whatever your initial amount is, times e raised to this k that they've already calculated, times t will tell you how much or how old your piece of material is. Okay. If, based on this, they wanted you to find the half-life of carbon-14. Okay, well, we know we're going to be using this y sub 0 function that they gave us. So y sub 0, y sub 0 times e raised to the negative 0.1230. So all of this on the right will give me the half-life. Half-life means half of the original. Okay, this will equal, I want it to equal half of whatever my original amount was. That's what it's asked for with half-life. All right, same setup. We have 1/2 times y sub 0 times e. If we divide y sub 0 from both sides, we don't have to worry about it. So now all we're left with is 1/2 equals negative 0, well, jumping ahead, is negative 0.0001216 t. We have an exponential, solve for that unknown in the exponent. So we're going to take the natural log of both sides. Divide that constant away from t. And we work this out, and it becomes 5,700. And a word of caution on this, make sure it's natural log of 1/2 divided by this number. Don't take the natural log of 1/2 divided by the number all as one thing. It's only the natural log of that numerator. Okay, so make sure you're very clear on that when you're punching into your calculator, that the natural log is only applying to that piece in the numerator, not the denominator. Okay, so carbon-14, so what this is saying is carbon-14 has a half-life of 5,700 years. That's what we found. One more part B to this question, and we're done. Okay, all right. So same setup, but part B. Now we have a new substance, some charcoal from an ancient fire pit on Java. I don't know where Java's at. Contained 1/4 of the carbon-14 of a living sample the same size. Estimate the age of that charcoal. Okay, so again, we're going to start with our same setup. Y sub 0 times E, this formula they give us, 0.0001216 T. But they're saying it contained 1/4 of the carbon-14. So this isn't a half-life, it's not half of it, it's 1/4 of the original amount. So it's 1/4 of y sub 0. Then again, we're going to solve the same way. Y sub 0 divided by y sub 0 is 1, so we don't have to worry about that. Should be getting comfortable now. We know we're going to take natural logs. So we're going to have natural log of 1/4 divided by negative 0.0001216 equals T, and it ends up being 11,400. So what this is saying is that charcoal is 11,400 years old. Okay, so this is all off of exponential functions, solving for an unknown, but being able to solve for that K or the T based on the data that's given to you. Okay, so Math Excel assignment is open. Take a look at that. It's not open yet? It's not?